the last part of this chapter, we're going to be looking at colligative properties. Colligative properties are properties that are related to the concentration of solute present, but it doesn't matter what the solute is. So we're just looking at how much solute is in solution and how that affects osmotic pressure, vapor pressure, boiling point, and melting point. So we've already talked about vapor pressure and boiling point in chapter 11. And what those are, but now we're going to see how the concentration of the solute in the solution affects those properties. So first we're going to start with osmotic pressure. So osmosis is just the flow of a solvent through a semipermeable membrane. Some substances form semipermeable membranes, and it allows for small molecules to pass through them. So you've probably heard this more in biology than anything, but let me just give you an example here. Okay, so here's the semipermeable membrane in the middle, and on the left side we have pure solvent. On the right side we have our solution. So we have a solute dissolved into the solvent. So water is able to flow through the semipermeable membrane, but the solute is not able to. It's larger and it cannot go through. And a solution of lower solute concentration, it flows from a solution of lower solute concentration to a solution of higher solute concentration. So you can see in the picture, the water is going through the semipermeable membrane to the other side. So it flows to the higher concentration of solute. Now, if we apply pressure onto the side of the solution, it's going to force the water to go back through the semipermeable membrane, and then we can equalize out the liquid levels again, and the pressure that is applied there is called osmotic pressure. And basically, once we do that, apply that pressure, and the fluid levels are equal, then that stops osmosis. So liquid is no longer able to flow through the semipermeable membrane, it just stops. So again, that's the amount of pressure applied to be able to do that. So this looks a little bit different, but it's very similar to what we've already learned with PV equals nRT. I want you to, let's see here, ignore Van Hoff factor. So just mark out I. We're not going to be using that with osmotic pressure. Okay. So let me rewrite this like this. So this is osmotic pressure, not pi. Okay. Osmotic pressure is equal to concentration, molarity, times R, which is the same R that we used in PV equals nRT, times T. Okay. So M times R times T. That's what's going to give us the osmotic pressure value. So let's look at our example here. It says the non-volatile, non-electrolyte glycerin is soluble in water. Okay, so I just want to point out a few things here. Non-volatile means it does not evaporate. So that's important. Non-electrolyte means if I put it into water, it's not going to dissociate. Okay, so that's important as well. Calculate the osmotic pressure generated when 15.8 grams of glycerol is dissolved in 235 mils of an aqueous solution at 298 Kelvin. So let's go back to this. So we need molarity. So molarity is just moles divided by liters. Okay, so in the problem, they give us grams, right? 15.8 grams of glycerol. So I need moles. So I'm going to divide by the molar mass, which is 92.09 grams per mole. That gives us 0.172 moles. Okay. And then it said we have 235 mils, so we just had to change that to liters. So 0.172 moles divided by our liters. So we divide that by 1,000 to get 0.235 liters. And so our concentration is 0.73 molar. Okay, so we have M, we have R, and we have T. So we have all three of those now. So I'm going to plug in 0.73. times R, 0.08206 times T is 298 Kelvin. Okay, so everything's going to cancel out except for ATM. And we calculate and we get 17.8 ATM is our osmotic pressure. Okay, now vapor pressure we looked at in chapter 11, and we saw that as the molecules evaporated, so the pure solvent is what we looked at. As the molecules evaporated, our vapor pressure increased until it reached a dynamic equilibrium where we had vaporization and condensation occurring at the same rate. Okay, but that was for a pure liquid. Now we're going to toss in some solute and see what happens and how it changes. So if I add a non-volatile solute, so again, that just means it's not going to evaporate, the solute stabilizes the solvent. So the interactions between the solute and the solvent are stronger, and so it's less likely for the liquid molecule to move to the gas phase. So adding a solid solute decreases our vapor pressure. Okay. So added solute decreases our vapor pressure. And we can calculate how much lower the vapor pressure is going to be using Raoult's law. And again, we're not going to be using Van Hoff factor here, so just mark that out, mark I out. And we're just going to do the vapor pressure of the solution is equal to the vapor pressure of the pure solvent times mole fraction of the solvent. Okay, so be careful here, because the mole fraction is going to be for the solvent. So circle that, because usually when we do mole fraction, it seems like we usually find the mole fraction of the solute. But here, it's for the solvent. Okay, so let's put that practice here. Okay, we have glycerin. Again, a non-volatile, non-electrolyte, and it has a density of 1.26 grams per mil. Calculate the vapor pressure at 25 degrees Celsius of a solution made by adding 50 mils of glycerin to 500 mils of water. The vapor pressure of pure water at 25 degrees Celsius is 23.8 torr. Okay, so we've got a little bit to do here. So we can't just multiply two numbers and be done. Okay, they didn't give us grams, right, to find mole fraction. They gave us volume. So we're going to have to work with that. So we have, vapor pressure of the solution, that's what we're looking for, is equal to vapor pressure of the pure solvent. So this number has to be given, unless this is the one I'm solving for, but the vapor pressure of the pure solvent has to be given and the mole fraction of the solvent. Okay, so the vapor pressure of the pure solvent is in the problem. It's 23.8 torr. But we need to find the mole fraction of the solvent. Actually, before we do that, let's change everything from mils to grams to moles, and then we can find mole fraction. So first up, we have 50 mils of glycerin, and it says the density is 1.26 grams per mil. So I needed to get it to grams, so I can go from grams to moles using molar mass. So I do that using density. So the density is 1.26 grams per mil. So mils cancel, that gives me grams. But I'm going to go ahead and add in my molar mass step and go from grams to moles. So molar mass of glycerin is 92.1. So grams cancels, and that gives me moles of glycerin, which is 0.684 moles. Okay, we're going to do the same thing for water. Water is always easy because its density is 1 gram per mil. So 50 mils is really just 50 grams. So 1 gram per mil gives us 50 grams. And then we've got to find the moles. So we're going to divide that by the molar mass of water. grams cancels, and that gives me 27.8 moles of our water. Okay, so now that we have moles of our solute and our solvent, now we can find the mole fraction and then plug it into our equation. So I'm out of room here. Okay, so mole fraction of our solvent. So we're going to take the moles of our solvent, 27.8, divided by the total moles, 27.8 plus 0.684. And we get a mole fraction of 0.976. Okay, so there's no units on that. Now we're going to find the vapor pressure of our solution. So we take 0.976, the mole fraction, times the vapor pressure of our pure water, 23.8. Okay, so if the vapor pressure of pure water is 23.8, then that means our answer should be lower, right? Because when we add the solute, it decreases the vapor pressure. And that's exactly what happened. So 23.2 is